Hi, everyone. Good morning. Good afternoon. We'll go ahead and get started in a little bit. We'll allow about 30 seconds to a minute for folks to trickle in. All right, we will go ahead and kick off. So hi, everyone. Welcome to today's Ask Me Anything session focused on the Ignite radar subtopic, low-cost millimeter and centimeter wave radar for planetary exploration vehicles. My name is Beth Vacarezza, and I'm part of the NASA SBIR Ignite team through my work at BMNT, where we help companies navigate to and through the Ignite process and unlock commercial opportunities both in space and terrestrially. Before we dive in, just a couple housekeeping items. So first, the session, as you will have heard when you joined, is being recorded and it will be posted to the Ignite website shortly after we conclude today. Please do use the Q&A box to submit your questions. Upvote the ones that you want answered, and we'll get through as many as we can, ideally all of them. And we will also be launching a couple polls throughout this session. Your input helps us to tailor these AMAs to you. So please do jump in and respond. We appreciate it. And if you missed last week on Tuesdays, Keys to a Winning Ignite Proposal Ask Me Anything session, the recording is now available on the Ignite website. So please do review that, as it provides more detailed information on the Ignite proposal process, as well as some lessons learned from past winners. So now I'll turn it over to Dave Truitt, SBIR Center Liaison to Marshall Space Flight Center, to give you a quick refresher on Ignite before we turn it over to our subtopic author. Dave.
Thank you, Beth. Thank you to Beth and her team for hosting this event. Thank you to our topic authors and team members for joining as well and providing their input and expertise. And to our attendees and potential applicants, we thank you for joining as well. We think this will be very beneficial for you. So appreciate you being here today. So real quick, like Beth said, we're going to do a quick overview of SBIR Ignite for those that may be new to it. And if we go to our next slide, we'll start with the differences in Ignite program versus mainline SBIR. Now, while infusion is always part of our goals for SBIR programs, Ignite focuses on commercialization with an intent to get technology and solutions into the commercial market as quickly as possible. We go through that, we accomplish that through smaller cohorts, entrepreneurial engagement, and accelerated schedules. You want to note that mainline SBIR, where it has typically over 200 awards, Ignite has typically ranged between 9 to 12 awards, and this year we're planning for 15. So you'll see that Ignite is much more competitive of a cohort. We're going to talk on another slide about BMNT's Slack channel and the opportunities there for community engagement. And we should also note that for Ignite, we have an accelerated schedule compared to mainline. Phase 2 proposals will be due at the 4th month of Phase 1 period of performance if you are awarded. And for Phase 2 periods of performance, we do encourage you to shorten beyond the allowed 24 months. So all good things to keep in mind for Ignite. Next slide, we're going to give you an overview of the Ignite program phases. You'll see it has 3 phases, very just exact same as mainline SBIR. Phase 1, 6 months up to $150,000. Phase 2, 24 months up to $850,000. And then Phase 3, which is non-SBIR funding if awarded. Note the 2 smaller boxes. We have I-Corps, Innovation Corps through National Science Foundation, which is their entrepreneurial training. If you apply and are awarded for that, that funding will be awarded in addition to the $150,000. We also have TABA, Technical and Business Assistance, which can be awarded to Phase 1 up to $6,500 in addition to the $150,000, and Phase 2 up to $50,000 for, or in addition to the $850,000. And of course, there are post-Phase 2 opportunities in addition to Phase 3. majority of which require matching funding, with the exception of phase 2 sequentials, which are not routine, but there are opportunities for that from time to time where you can get additional funding. So next slide, we're going to look at some key dates for Ignite. You'll notice June 2nd is when the solicitation became live. So we are in communications blackout for that. So we cannot answer specific questions about your proposals. And also note the 22nd of July at 5 p.m. Eastern Time is when solicitations will close. And we expect awards to be announced late fall of 2025. So should be November, December timeframe. And I believe our last slide will be how you can join our community and stay in touch with current events. I'm pretty sure that'll be the next slide. There we go. So you can go to our NASA SBIR website and sign up for a newsletter, which we strongly encourage you to do. Also at that website, if you go to the Ignite link, you will be able to get the recordings for all of these AMAs that we have hosted. We also have a BMT Slack channel that you can join and stay abreast of community building activities. And of course, NASA is not the only SBIR game in town. You can go to sbir.gov and learn about the other federal agencies that participate in the SBIR and STTR programs. So that is it for our overview. I think we'll have time for some questions now. I'll turn it back over to Beth for that.
Thanks, Dave. No questions about Ignite generally, but if we do have some at the end, we will certainly bring you back on. Thank you.
Fantastic. Thank you.
All right. So now we'll hear from the subtopic author behind this radar subtopic. So we'll invite Terry Fong, Chief Roboticist in the Intelligent Robotics Group at NASA Ames Research Center. So Terry, over to you.
Great, thanks so much. Good morning, good afternoon. Hopefully not good evening to everybody, at least not yet. As Beth said, I do work at NASA Ames. I've had a number of roles throughout the years at NASA, and currently I'm splitting my time between work at NASA Ames and work at headquarters. And today, actually, I'm going to be speaking to you from my headquarters role, which is the Technical Integration Manager for Autonomous Systems and Robotics within part of the NASA Space Technology Mission Directorate. And so here we're talking about the subtopic on low-cost millimeter and centimeter wave radar for planetary exploration vehicles. If we could go forward a slide. This is just a quick summary of what's actually in the topic description here. But just to get into this here, NASA is interested in radar for planetary exploration vehicles for a few reasons. One is because of radar's potential to provide ultra-precise positioning and navigation across a range of environments. The second is, in fact, the fact that we can look at radar as compensating or basically overcoming limitations that we see both with optical sensors, particularly in a range of very challenging illumination conditions, like on the moon, for example. There are areas that we're interested in that are at high latitudes, so near the poles, where we have very difficult imaging conditions because the sun is a low angle, just barely across the horizon. But radar also can overcome limitations of sensors which are commonly used with mobile vehicles, at least here on Earth, which is LiDAR. Places like the moon, for example, have lots of dust, levitated dust, poses a problem to all optical sensors, cameras, and LiDAR, and anything else. And so one of the things we're interested in is how can we make use of other sensing modalities, such as radar, to overcome those limitations. Now, in terms of planetary exploration vehicles, and we'll get into this in a little bit more in the next slide here, we are interested in how radar can be used for a number of different applications. One certainly is the area of 3D terrain mapping and modeling. That is, how can we perceive and reconstruct the physical terrain around these vehicles, whether they're vehicles on surface or above surface. The second is in terms of geometric hazard detection. Certainly there can be hazards from the terrain. On the moon, for example, rocks and craters and slope discontinuities are geometric hazards, but also things like people moving around. So, astronauts in suits or vehicles. We have plans for human exploration where we have a number of different vehicles, some transporting humans, others just moving cargo around, for example. And of course, there are, will be man-made structures that are deployed or assembled or constructed in some manner on these surfaces. A couple other areas are in terms of position estimation. That is, can we understand by the use of radar maybe combined with other sensors, what is the absolute position of this vehicle that we might have the sensor on, or relative positioning, to a particular location or feature of interest. And then you combine all these together and try to understand how can radars really support just overall surface and suborbital navigation, where you do have a combination of hazard detection, position estimation, maybe the way this feeds into things like path planning or path following. Next slide. So the subtopic itself is focused on low-cost millimeter wave and centimeter wave radar systems. It is not focused generally on navigation sensors. So we're not looking for LiDAR, we're not looking for new cameras, we're really focused on radar. And one of the reasons for that is because there's been a lot of development over the past several years in millimeter, centimeter wave radar for self-driving cars here on Earth. NASA is very interested in understanding, can any of the commercial technologies being developed for those kinds of applications be applied to space? And if so, what's required to do that? Does that require basically adaptation in some manner? Does it require some custom hardening in order to make it work in planetary environments? Or maybe they are just happen to be suitable, especially for perhaps short duration, maybe not safety critical applications, where you could just basically take an existing terrestrial sensor and reuse it in space. We are in particularly interested in the proposals that to develop radar systems not just as a standalone sensor, but that can support at least two different capabilities. And these mirror what I talked about on the previous chart here in terms of positioning, navigation timing, in terms of dynamic and static hazard detection, in terms of object tracking. So if you're looking at following, for example, suited astronauts on the surface or other vehicles, and of course, 3D terrain mapping. Now, I think that one of the things about this program, and this is true, I think, across the board for SBIR, but especially true for Ignite here, is it is important for us to understand how the proposed system could be applied to enable Earth-based applications. And of course, the parallel to planetary exploration vehicles are on Earth, cars, unmanned vehicles for either people transport or cargo transport at various scales. And then, of course, for NASA, we're interested in hearing people's thoughts of the applications for NASA-specific uses. NASA has a lot of work going on right now to develop future astronaut vehicles. So, for example, the Lunar Terrain Vehicle is a system under development right now by 3 different companies, basically creating the next sort of astronaut Jeep for the moon. We also have a long history of NASA of fielding planetary rovers. Many of you are probably familiar with Perseverance, which has been on Mars for a number of years, or the Viper rover, which was under development for the past several years for the moon. But then also NASA has been developing flying systems, Ingenuity, the helicopter in Mars, or Dragonfly, the flying system that's going to go to Titan. These are kinds of systems, all of these here, that involve basically mobile vehicles operating on or near surface of places like the moon, Mars, and other planetary bodies. So if we could move on here, I'll give you a little bit more detail for those of you who are not, I think, really focused on the development of these kinds of systems here, of how we're trying to look at sensors. So next chart. This will be an overview of one mission. I'm not hearing audio. Is there, Beth, is there audio that can be shared?
I'm not hearing any either. So one moment.
That's okay. I can narrate here. So this is a overview video of the Viper lunar rover mission, which was under development for the past several years, basically since 2019 at NASA. It's a mission that was designed to go prospect for subsurface water ice, so underground water ice at the polar regions of the moon. And in particular, targeting an area near Nobile crater, where there's a combination of interesting conditions, one of which has to do with areas that are never illuminated, so areas that we call permanently shadowed regions. So Viper as a mission was designed to land and then to prospect over about 120 days, driving about 20-kilometer total distance, including a variety of regions, going into permanently shadowed craters and using a drill and a number of different onboard instruments to basically prospect for underground water ice. Now, the kinds of things you run into, of course, have to do with how does this robot actually manage to navigate in such a difficult environment. Places where you see, for example, the sun and the earth are low to the horizon, which leads to long cast shadows, makes it difficult to actually determine where there are hazards. Are there rocks? Are there craters that pose a challenge to the vehicle's ability to drive across the terrain? All kinds of questions of, how do you cope with the fact that beyond the illumination conditions, you do have levitated dust by the rover, for example, as it's driving. And how do you really assess the danger of moving from point to point as you're trying to do this in the most efficient and frankly speediest manner possible? And the answer, of course, has to do with the navigation system. Has to do with what kind of sensors do you have on board for positioning and for hazard detection and terrain modeling. All the things I talked about a couple slides ago. So next chart. Yeah, so Viper as a mission, just to give you an idea, is a mission that requires being able to support a fairly long distance of traverse. So that means that any sensors on board have to be robust enough to be riding on board a vehicle. They're not just on an orbiting spacecraft where you don't have to worry about shock and vibration. It certainly is a kind of situation where you do have to worry about extreme temperature regimes. Now, this is not saying the sensor itself has to be able to survive 40 Kelvin to 300 Kelvin, because of course the vehicle that it's carried on, whether it's a planetary rover or a human transport vehicle, can provide some temperature management. It has to be able, on the other hand, to be able to survive operation across a variety of speeds, depending on the kind of vehicle you have. Viper is a slow-moving planetary rover, so that's about 20 centimeters per second maximum speed. It's very slow compared to things we see on Earth. On the other hand, the lunar terrain vehicle is meant to be the equivalent of basically like a golf cart. So driving, perhaps 20 kilometers per hour. And as a result of that, there are different sort of ranges of speeds that you have to contend with. Next chart. One of the things about Viper is that it has to operate in a variety of modes. One of those modes is rapidly moving from point to point, basically getting from where you are to where you'd like to be to actually spend more time doing detailed surface work. And so there's a question of this for sensors that support navigation of, can you support like far look ahead? Are you looking ahead 100 meters, 200 meters? Are you looking at a focused area versus a wide area because you're trying to make decisions about driving efficiently around obstacles? Next chart. And then once you're in a location of interest, for example, an area that we might call a science station, where you want to do, for example, detailed sort of survey patterns and traversing back and forth. Here, you might have requirements that say you need to be able to precisely position yourself relative to features or to be able to steer around obstacles that could be particularly dense. And therefore, you have needs to have high resolution, high accuracy sensing of terrain features. Next chart. And I mentioned, at least for the moon, there's a lot of interest of being able to operate in areas where there is no illumination. So either illumination that comes from the sun or illumination carried on board. But the question is, can you operate with more active ranging? And that's really, I think, one of the fundamental reasons why NASA has interest in radar and its ability to operate independent of the visible illumination conditions. Next chart. And give you an idea of the kinds of environments that we're talking about, we're also interested in dealing with sort of these dynamic changing environments. This is an example of a traverse plan for Viper, the idea that the rover would land and move. And what you see here is a visualization of the illumination conditions. So as the sun moves and as we have shadows that come off of large terrain features, mountains in the distance or local craters causing shadowing, for a rover like Viper, which was designed to be solar powered, it has to basically do this kind of move and wait. You have to get to places sometimes and sit there for a long time before you're able to move on. Now, this is independent of what you would use for a radar sensor, but this is to give you an idea that on a mission, you're going to have to integrate the sensor and take into consideration all the other things that the mission is trying to accomplish. In this particular case, the motion is really driven by the fact that the solar powered electric vehicle and therefore needs in places of sun. But that also means that the sensor has to support the kind of movement and kind of assessment of when you get to a safe location, are you parked at the right location? Can you model the terrain accurately to say, yes, this is the right place to stop and wait until the sun comes back? Next chart. Just to give you a very brief overview about one of the other implications of these sensors is that, of course, the sensors provide data that's used both autonomously, that is on board a vehicle such as a Planetary rover, but also by mission control, that is operations. And that's true whether or not we're talking about a robotic vehicle or a human exploration mission. So as an example, this is a snapshot of an operational simulation for Viper at NASA Ames. And here's the Mission Control Center. Next chart. In the front row of this mission operations team is a set of operators called the drive team, which involves a real-time scientist, a driver, a co-driver, navigator. They're all looking at data that comes back from the vehicle, including all the data from the navigation sensors, which for Viper was primarily camera systems, and then augmented by other sensors such as an inertial measurement unit and a star tracker. They're using all this information to make real-time decisions from a science point of view, as well as from an operational point of view of how to drive the vehicle. Next chart. One way of doing that is by taking all this information and fusing it into operator interfaces, such as the one you see here, where you have representation of hazards. So in the center of there's a hazard map. Green is an area that's considered benign for the vehicle. Red is an area considered to be very hazardous, and so stay away from that. So you're basically taking information from sensors, you're turning that into, for example, a set of point clouds that you assess and look at in terms of roughness and step discontinuities, slope, and all those kinds of things. And then you're visualizing that in terms of a 3D colored map representation and using that to make real-time decisions from a human operator point of view. Next chart. And so what you see here is an operator trying to assess the terrain, figuring out where to next send the vehicle, understanding relative to the vehicle, where are there terrain hazards, these, for example, red areas, and positioning carefully a location, a waypoint to send the vehicle. So the vehicle is stopped, you designate a waypoint, and next chart. And now you're taking a look at that location. You may look back at prior images, and if there were other data sets, so for example, data that came from radar, you might want to look at those in addition to these sort of secondary maps, which, again, are based on analysis of the data. You might actually want to go look at the raw data and then command the vehicle based on all that information to start moving, and do this kind of interactive command planning over and over and over again. These are the kinds of things where having better navigational information, better 3D environmental understanding are critically important to be very efficient and very effective for operations. In any case, all of that is to say is that NASA is interested in radar as a new kind of sensor modality that we currently do not use in space, but which we believe has a lot of potential for use in planetary exploration. So with that, Beth, I don't know how you want to handle the Q&A, but I'm happy to answer questions.
Excellent. Thanks, Terry. We will just go down the line of what's come in. I'll start with the thumbs up questions first, but okay. we'll have time to move through all of them, I do believe. So when you say low cost, do you have specifics on expected cost of this sensor, or can you speak more generally to kind of your cost?
Yeah, there's a couple ways to think about that. One is low cost means that NASA is not interested in for a specific mission investing in a single-use bespoke sensor. That is, we don't want to say, yeah, we understand that there's technology in an area, let's now customize this and spend many years creating the perfect single one-off sensor. So for low cost, in this case here, we're interested, as I said earlier, in the potential of making use of terrestrial commercial technology. So if there are automotive grade components that could be used as is or with minor modifications, to us, that's considered to be low cost. The other way to think about this too is that if you look at the way flight systems for space missions have been developed in the past, you might look at a camera system, just like a camera. A single camera could cost upwards of $1 million or $2 million per camera system. And so we're not looking to spend millions of dollars, but in terms of like specifics, is it like 5 cents? Is it $500? I don't know, but we're not looking for these really sort of, as I said, bespoke, custom, one-off kind of things, which carry a large price tag. Large meaning in the millions of dollars.
Great, thank you. The next question is, do you have a certain detection range requirement for NASA applications?
So the call was described as addressing a number of different planetary exploration vehicles, which have different operational characteristics. So a planetary rover is going to drive perhaps 10, 20 centimeters per second. And you can figure out, okay, how far ahead you need to look in order to be able to stop based on moving at top speed in the worst conditions. That may be on the orders of meters, maybe hundreds of meters. Contrast that with a flying vehicle, or say an astronaut vehicle that's driving at say 20 kilometers an hour, and of course that changes the range itself. So there's not a single range. I would say in general, though, we're probably talking on the orders of dozens of meters to perhaps several hundred meters, but certainly we're not interested in kilometer or really longer ranges, because we're talking about vehicles on the surface or near the surface.
Great, thank you. Do you have power consumption constraints?
Well, for all spacecraft, power is probably the biggest thing. Well, power and mass are really the things that are always come back from a system engineering point of view to bite you, because you can never have enough power, you can never have enough mass to put your system in. So in general terms, we are more interested in lower power systems overall, and that's both in terms of just survival, if it needs to be powered on in some way to survive, or just in a quiescent state, versus sort of active use. Just in general, lower is better.
Is there an interest in leveraging COTS radar transceiver chips?
Absolutely. I think one of the things about SBIR that I've always been excited about is the fact that it is targeted as dual use. So commercial applications and government applications. From the government side, NASA, of course, is interested in flying things in space. But until we have, an equivalent of what we have here on Earth for all sorts of industries, it's still going to be a very specialized area. And so for us, anything that focuses on dual use, where the dual part really is space as the dual, the primary application is maybe commercial terrestrial use, such as COTS components, transceivers, or even integrated full systems. We are very much interested in that.
Is there a platform-dependent preference for electrical versus mechanical steering of the radar antenna array?
I don't think there's a preference from a NASA point of view. I think, again, just like I was saying earlier, different platforms, different exploration vehicles have different requirements themselves, and even the same vehicle used for different missions or different tasks might have different requirements as well. So I don't know if there's anything that I could say about preferences for mechanical versus non-mechanical steering. I think in general terms, flexibility and the ability to steer, and of course there are all kinds of questions of are you talking about the rate, the precision, how well can you hold while the rest of the system is under shock and vibration. I mean, those are all to be honest, there's single use specific questions. So there's not one answer that I can give for that.
Great, thank you. Are there certain frequencies that would be preferred for radar operation on the moon?
No, we're interested in hearing what people think. We targeted, centimeter and millimeter wave radar because there is certainly a lot of interest and development commercially on terrestrial here on Earth for applications such as self-driving cars. I think we're really interested in, really how can NASA, best leverage those investments to date. There's not a specific thing that I'm aware of in terms of like frequency.
Okay, great. Next one is, what are the rad hard requirements for the radar?
Yeah, so again, there are a lot of specifics that have to do with where are you deploying a particular system. Obviously, the radiation requirements for the moon is quite different from Mars, is quite different from, say, Titan or Europa. I think that right now the interest of NASA is, and it has been for several years now, is focused on returning to the moon and then going to Mars, at least in terms of like expanded human exploration. We of course have had lunar exploration and Mars exploration using robots, but we're interested in doing this with humans. So in terms of near-term priorities for NASA, it really is focused on like lunar surface, and you can You can find lunar surface characteristics, in lots of different reference places.
Okay, thank you. There's another question that is about targeted distance you're looking for, which we have answered previously. If there's any edits to or amendments, Terry, that you want to add to that answer, please do feel free to chip in. But if not, we'll move to the next question, which is, do you have any safety certification requirements for the sensor at the end of phase 2?
Yeah, and I apologize for saying, well, it depends, because I think I'm trying to wear my engineer's hat, which is that it depends on the application. Obviously, if you're trying to operate in and around humans, especially those humans, might be, close to wherever the sensor is actively scanning, then certainly there are going to be any, questions about the safety of that sensor. I think in the case of purely robotic missions, so these are planetary rovers or flying vehicles for robotic exploration, there may be less in terms of safety, although we are always concerned about the potential for risk to the vehicle itself. Is there anything that the operation of a device on board a planetary rover might lead to potential loss of the rover?
Great, thank you.
Mhm.
Next question, we may need to pull in Dave, but could you please share documents or resources with the targeted key specs? So for example, radar field of view, resolution, range, size, power. I do believe specifications will be available in the solicitation itself. But Dave, Terry, please do feel free to jump in with further specs.
Dave, do you want to comment first?
No, you go ahead. I was going to defer to Haley, so I'll defer to you.
Yeah. The topic itself, as I said, addresses a broad range of platforms. That is, we're looking at slow-moving planetary rovers, such as Viper or Curiosity or Perseverance, as well as higher-speed surface vehicles like the Lunar Terrain Vehicle. We are also interested in how these could support things like the Ingenuity helicopter on Mars, as well as the Titan flying vehicle called Dragonfly. So all of those have different requirements in terms of things like what is the available size, weight, power constraints for adding on navigation sensors. But the same thing is true here on Earth. I mean, putting something on a golf cart is different than putting it on a semi truck. It's different than putting it on a drone, a small drone, versus putting it on a large drone. I think NASA recognizes there's not a single application that says, okay, there's a universal widget that supports all of these things. And so we are interested in understanding where can we make best use of commercial technologies, and ones that are maybe tailored or adapted from terrestrial applications to perhaps a subset of those applications in space. So if you have a sensor that you say, hey, this is perfect for all planetary rovers that are moving at 20 centimeters per second and are the size of a golf cart, that's a perfectly valid application use case area, and we would be interested in that. If you have something that intersects a number of these different vehicles or different applications or different sort of constraints, we'd just like to understand what are those limitations.
Great, thank you. How much processing of the radar image is desirable? Is it better to provide raw data that the rover can process, or a more refined image?
So with all sensors and instruments to date on planetary exploration rovers, there has always been an interest in both the raw and any sort of processed or derived data. And that's because, generally speaking, we use all available data for science, and so there's not always this understanding ahead of time of what might be useful. And so having access or the ability to access raw data is always of interest to NASA. That said, if you are trying to support a specific function, such as high-speed detection of terrain hazards, maybe you don't really care about all the information about the 3D high density point clouds, and all you care about is like, oh, there's something dangerous that's forward 2 meters and left 1 meter. And so I do think that we are interested in solutions that can provide both raw and derived data.
Great, thank you. Let's see. So is there interest, or excuse me, no, I'll continue with that question. Sorry. Is there interest in a deployable fixed wing aircraft for Mars environment in which an electronically steerable phased array is embedded on the lower wing surface? If so, where should we primarily focus? Radar, electronics, performance, or the complex mechanical packaging of the array? And I'll say specifics about kind of what companies should or should not do cannot necessarily be provided in this session, but if we can kind of generalize an answer, Terry, for I suppose kind of reconfirming what generally you're interested in seeing.
Yeah, so the topic here is radar for planetary exploration vehicles. It's not, radar for a specific vehicle, for a specific mission, for a specific, platform. And so I cannot comment as to what NASA's priorities are for, near-term missions, be it, fixed-wing aircraft for, places that have atmosphere, or rovers that are in places that are just driving on the surface. We are interested in radar in terms of its capabilities. We're interested in radar in terms of the possibility of leveraging terrestrial commercial investments that will help us make use of a sensor that is lower cost to these one-off custom kind of systems. I think that it's certainly up to any of the potential proposers to make a case that there is something that would be beneficial for particular applications, whether these are on surface or above surface, whether they are fast moving or slow moving. This is not a call for a single specific mission. This is a call for technology development.
When you say raw data from the radar, is it point cloud data or the ADC data?
Again, I think it probably depends on who you ask. If you're trying to use radar as something that's a modality for science measurements, the answer is going to be, hey, whatever is the lowest level data that's available. If you're thinking of this from a navigation point of view, you might be interested in point clouds. And so I think that there's not a single right answer here. I think in just general terms, having more than just derived final output is of interest, because there are always things we can do, especially from a science point of view, to make use of measurement data that comes off of a sensor. That said, I will point out that this call here is not a science instrument call. It is specifically supporting the applications I talked about, such as 3D terrain mapping and modeling, hazard detection, navigation.
Next question is, and again, we'll kind of generalize this, what is the right amount or type of work to try to do in phase 1 versus phase 2? So I suppose perhaps a different way of phrasing that would be, by the end of phase 1, by the end of phase 2, what's the ideal presentation?
Well, maybe a program response would be appropriate first.
Yeah.
Dave and Haley for this?
I'm not saying yet. Official response is look for the solicitation on the SAM.gov link. We feel like we're pretty clear on what we're looking for there, because us specifically telling you the exact type of work that needs to be done won't be appropriate. But like we mentioned at the beginning, Ignite is looking for high TRL commercial ready applications. So that's an unofficial answer, but please see the solicitation.
And Dave, while we have you spotlit, how many awards do you envision for this topic, or generally for the Ignite subtopics?
Yes, I think we covered that in one of the earlier slides, but typically we've awarded between 9 and 12 proposals for Ignite, and this year we are targeting 15 awards.
Great, thank you.
Yep.
So this next question, we already answered it. So again, it's asking whether it's ideal for a submitter to target a specific rover platform. So that response was provided probably within 3 questions ago. So we'll go ahead and move to the next one, which is, if you have a product available now that effectively is phase 2 ready, can you submit direct to phase 2? And perhaps we'll need to bring Dave or Haley back up for this question. So is direct
Yes,
to phase 2 an option is the question.
right. Unfortunately, direct phase 2 is not an option for NASA SBIR at the time. I know some other agencies have it, but we're not quite there yet.
Great, thank you. Okay, and there are just a couple questions that did come through from folks' registration questionnaire. So I'll ask just a couple. So one question is, are there options to present a solution that meets most of the requirements, but not all? And by options, I suppose the submitter is getting at, will that proposal be in the running, so to speak?
So I think that in terms of like the functionality of what the sensor is capable of supporting, the topic description says that NASA highly prefers systems that can address, and there was a specific list there. So I would refer people back to that. There's not a requirement in there, I believe, that says you must support all of them, or even like a specific number of them or specific ones, but certainly NASA has preference.
Are there specific NASA hardware or software systems that the new radar solution will need to be interfaced or compatible with?
So again, this is not for a specific mission for which we would point you to specifics in terms of any sort of interface kind of documentation, or specifics in terms of how this would fit into the engineering of a specific platform. So I do think that NASA in general is interested in solutions that support easy integration to different kinds of systems. So to the extent to which there are any sort of existing common space standards or interoperability standards that you could point to, or that are in process of being development, given there has been a lot of interest in commercial use of space, that's probably the right approach there. But there's not a specific thing that I think we should point you to right now, because again, this is not for a specific single mission or platform.
The next question asks, is this call restricted to organizations with specific NEXT codes? So perhaps Dave or Haley, I'll bring you up for this one.
Yeah, the specific NAICS codes are listed in the solicitation.
Great. All signs point back toward, many signs point back toward the solicitation. Thank you. Terry, are you able to speak at all to the applications that NASA foresees for computer vision and radar?
For computer vision and radar. So, as I showed during the slides here, we are interested in the ability for vehicles, and this is both robotic ones as well as ones that carry humans, to be able to be very safe, efficient, and effective in their ability to move across planetary surfaces or above planetary surfaces. And so, the thing that really I think drives us is our ability to improve the way that happens. And we do have limitations with the use of camera systems, both in terms of the kinds of information they can gather about the environment, and of course, what effort is required to actually process, for example, say stereo imagery into useful derived products for navigation. We recognize that other sensors such as LiDAR and radar may also play a complementary supplemental role in the navigation solution. So we're not saying that there has to be a single perfect sensor that does everything. And as a result of that, it certainly is the case that you could consider, how does a radar sensor fit into the class of navigation sensors that exist and have been used to date, which covers things like cameras and star trackers, inertial measurement units, wheel odometry, those kinds of things. We're not looking for a single solution that fits in this little tiny box and costs $0 and does everything. But we're better trying to understand how this technology could really help accelerate the ability for us to operate vehicles in a wider range of environmental conditions faster and more safely.
The next question asks about JPL. So are they involved at all with this subtopic? If you can speak to that.
I'm not really sure what the question is asking for. I mean, this is a NASA SBIR call. JPL is involved with technology development missions, just like most, if not all, of the NASA centers.
The next question is having pre-seed VC funding a deterrent for acceptance to the NASA SBIR Ignite, given our pre-seed funding is about 10x as much, I assume 10x as much as the phase 1. So I think Haley and Dave, I'll volley this question over to you, and I'm happy to repeat it if helpful.
I can take that one, Beth. If you'll look through like the review criteria and the rubric, you'll see that we are interested in seeing firms that have investment or are able to bring in investment or have strong plans for how they will achieve that investment. So without knowing kind of the specifics of your situation, I would just point you to those sections of the solicitation to read through those in more detail.
Thanks, Haley. So there was a follow-up on the JPL question, which is just to say JPL is investigating our existing solution. And the point of the question was to understand if this was related or helps with the company's submission. So,
Dave, do you want to comment on that from an SBIR program point of view?
Yeah, I'll defer to Haley on that.
Okay.
We review the proposals as received, and that's the information that we use to evaluate the technologies that are being proposed. We don't use outside information.
Great. Well, if folks have last minute questions, please do feel free to submit them into the Q&A. All right, nicely timed. So are proposals reviewed individually or against each other? So Haley.
The details about how we actually perform the review, I hate to say this again, but it is listed in our solicitation. It goes through the steps that we use to evaluate those proposals.
And again, the solicitation can be found, of course, through the link provided in the chat earlier in this session, as well as on the Ignite website. So please do head to the Ignite website. So any final comment, Terry, from you before we close out today's session?
My only comment is that we put this out there as a topic because we see a lot of interest in development in terms of terrestrial applications, as I said, particularly related to self-driving cars. NASA is very interested in the potential of radar to address the limitations that we have with cameras and even with LiDAR, which is still largely in development for planetary rovers. And so we're kind of like jumping ahead to saying, hey, what else can really assist in our ability to operate these vehicles faster, safely in a wide range of environments like the moon, Mars, and beyond. So encourage anyone and everybody who's online today, if you have an idea of how to develop the sensor technology and how it can be used both on Earth and in space, please submit.
And with that, we will close today's session. So Terry, thank you so much. Proposals are due by July 22nd. So again, head to the Ignite website or head to the link linked in the chat, and also join the Ignite Slack workplace to stay connected and ask follow-up questions. So Terry, again, thank you so much. Dave and Haley and the rest of the Ignite team, thank you. And thank you all for joining us. We look forward to seeing your proposals. Bye.